Hello everybody, welcome to the latest edition of the Physics Corner with your host, Dr. Christopher Sorolla. Today we're taking a look at RMS voltage and RMS current. So, one of the things that you've learned, or hopefully have learned by now, is that when we have an alternating current or alternating voltage in play, that the current and voltage both go up and down, which is to say, at some points in their cycles they're positive, and other points that they're negative. And what that means is that if you take a straight up average of either the voltage or the current over time, you get zero, which doesn't make sense in practice because, of course, you can get things happening when you, say, plug a socket into a device into an outlet at home, right? That's what you're pulling is alternating current and alternating voltage. So what do? Well, the short version, which your instructors will have also talked about, is that you square the voltage or the current, and then you take the square root, which sounds kind of a weird way to do things, right? Because aren't you undoing what you did before? But remember that taking a square root is only going to give you a positive number. And therefore, what was a positive or negative number becomes only positive. And this is called RMS, or root mean square, as in root average squared voltage and RMS current. And that is a better way to talk about what's actually happening. So let's put that to practice. So let's imagine we have a source of alternating voltage. You can imagine, say, this is coming out of your wall socket with a peak voltage of 170 volts, and it's used to operate a device that is working at a 15 amp RMS. So my questions are, what's the RMS voltage? What's the peak current? And what is the resistance of our device? So let's go ahead and calculate. All right, so to do a little bit of sketching just to kind of show off what this might look like, let's suppose we have voltage versus time, and we're plotting this. And as we were talking about before, that the voltage, because it's an alternating voltage, is going to be increasing and decreasing in a pattern like this. Now, it doesn't necessarily have to be a sine wave. That's not a law of nature or anything like that. But chances are, and in almost all practical applications, this is the simplest thing to do, and it's typically what actually is done. So we have voltage going up or down, and this then would be the peak voltage. So there's your peak, or maximum voltage, if you will, for that particular cycle. All right. Now again, also notice that the voltage reaches a maximum, which is a positive number, and bottoms out at the minimum as a negative number. Now, what that really means in practice is that the voltage is actually pushing one way versus another. So you can imagine, quote unquote, the voltage trying to push electrons to the right and then push them to the left, to the right, to the left, to the right, to the left, going back and forth like that indefinitely. As long as you've got the sources available and you've got your device plugged in, that's what you're doing, okay? So the idea of a negative versus positive is sort of a misnomer, if you will, in a sense, because it's really just referring to a direction. And I would submit that pushing things to the right is just as important and just as impactful as pushing them to the left. So when we do this idea of a root mean square, just to kind of show off again how that might look if we do this, again, what we do is we square and then take the square root. So squaring and taking the square root ends up giving you something that looks sort of like this. And so notice that the peak here, we squared it and took a square root, we get the same thing. But this section over here, we took and squared it. When you square a number, you get a positive number. Take a square root of a positive number and you get this. And so instead of having a up and down sort of behavior like this, we get two peaks like this. And again, this goes on consistently or indefinitely as long as you've got things plugged in. Now, the root mean square idea is then take an average over one full unit or one full cycle's worth of time. So we don't just simply take the peak here, or for that matter, the zeros over here, or a straight up numerical average. There's a special way to do this, which ends up roughly about here, called the RMS value. So RMS. Now, I'm drawing this for voltage, but you could also have this sort of discussion for current, and you get the same sort of idea. All right? So RMS current, RMS voltage, and the formula to transform from RMS current and peak current, or RMS voltage and peak voltage, looks like this. And it'll be the same thing regardless of whether you're talking about current or voltage. Now, also, by the way, and hopefully you've caught this already, when I talk about peak, whether it's a peak voltage or a peak current, another name for that is amplitude. So when you did waves and vibrations way back in mechanics, long ago at this point, you talked about the amplitude of a vibration or the amplitude of a wave. It's the same idea. This is really a wave phenomenon in a sense. And so we use the same language or very similar language. But when you did that, you probably didn't need to talk about RMS. Well, we need to talk about RMS here because we are interested in talking about how voltage and current actually impact things. They actually do make things happen. And if you took a straight up average, which would give you 0, it would make it look like nothing's going on. All right, so enough for the preliminaries. Let's talk about some unknowns and knowns for our problem. So we are given that the peak voltage, that should be a peak voltage, is 170 volts. We have a device operating at an RMS current of 15 amps. And our resistance, well, that's a question, isn't it? What are our unknowns then? Unknown, instead of getting a peak voltage, we're interested in the RMS voltage, so that's an unknown. We have the RMS current, we want the peak current. And we're going to assume that this particular device is only, or the source of voltage and the wires are only connected to a resistor. So there is some device with an effective resistance out there, and that's what we're looking at. One more thing to kind of sketch in very briefly, we can imagine we have a circuit diagram in the most simplest possible form. Looks something like this. So what are we looking at? Well, here's our resistor as we're used to talking about. Then we have our wires, of course. And then there's a symbol with a little wavy sign inside the circle. What's all that about? That is representing our AC, or alternating current voltage source. Okay? So the voltage is no longer direct current. So the difference between direct current and alternating current, direct current, one direction. You only would have voltage trying to push, quote unquote, current in one direction or one sense of direction along the circuit. In this case, the voltage is moving the current back and forth incessantly like this. And that's what the wave stands for, and that's what that's talking about. So the calculations are the easiest part of this problem. Most of it's sort of preliminary discussion. So how do we get RMS voltage if we're given a peak voltage? So RMS is equal to 1 over square root of 2 peak voltage, like this. So 1 over square root of 2, and our number was 170 volts, like that. If you do the calculation, I round off a little bit, 120 volts. This is not an accident for this problem. I chose these numbers on purpose, and that's to emphasize what's typically coming out of an average wall socket. So if you go to your house, your dorm room, your apartment, wherever you're at, and you plug in a TV, you plug in a lamp, you plug in a toaster, then this is the voltage that's driving what's happening. Okay, I will say that that's not the only possibility in a home. If you have something like a dryer, your average dryer needs a little bit more oomph to it, if you will, and those lines are typically 220 volts. But now that you know, 220 RMS volts is what that would be. All right, what if we need to swap it around? So in this case, we're given RMS. How do we find peak? Well, if this is the formula here, I need to multiply both sides by square root of 2, don't I? And so peak current will be square root of 2 multiplied by RMS current. So root 2 and 15 amps. There we go. And that will give us a total of 21.2 amps. So again, as always, I suggest everybody check my math, make sure everything's on the up and up. Okay. Last thing, we're assuming, let's suppose it's a toaster, just to throw out a sample. Let's suppose your toaster is drawing 15 amps of RMS current, and it's plugged into a wall socket of 120 RMS volts. What's the overall effective resistance of our toaster, or whatever device we're talking about? This is a version of Ohm's law, right? So Ohm's law, as we know from many times before, is V equals IR, right? Ohm's law turns out to be one of the most versatile types of formulas in all of physics, in that it can be used, or variations can be used, in all sorts of circumstances. How do we apply it to a AC circuit? Well, there's two different ways to talk about this. So for example, if you have the peak voltage, then the peak voltage is equal to the peak current multiplied by the resistance. Or if you have the RMS voltage, then it's equal to the RMS current multiplied by the resistance. Notice that the square root of 2 is present in both this and this when they relate to this and this, right? It's the same, so it wouldn't matter. Now, what you can't do is mix and match. You can't have RMS voltage and peak current and then resistance. Your number will be off by a factor of square root of 2, won't it? So just kind of a cautionary tale there. You want to make sure that these subscripts are matching up in order to make this play out. Also, again, I am talking only about an effective resistance for this device, whatever that device is. A separate video will discuss what might happen if we involve other things like capacitors or inductors. But for this particular episode, we're just doing resistors. And then resistance, I'll use the RMS versions, is voltage RMS. And to be quite honest, if you want to be very careful, we should put a little delta in front of that, right? And RMS current like this. We were given 120 volts, or we found out 120 volts, and we were given 15 amps. 120 divided by 15 is 8. And so this particular device will have an effective resistance or equivalent resistance of 8 ohms. And it's kind of that simple, right? So again, the math isn't too difficult, but it's worth having a short discussion and reminders of what RMS is all about and the difference between, say, peak and RMS and why that matters. As I said before, in a separate video, we'll talk about what happens when we add in capacitors and or inductors, but that's a separate discussion. All right, thanks everybody for your attention. Our technical support is Sidney Gautraw and Sophia Turner. We are funded by the University of Mississippi and University of Southern Mississippi. Everybody, I am Dr. Christopher Sorolla, your host, broadcasting from Hattiesburg, Mississippi, and clear skies.